Hey, thanks a lot, Alan. Can you all hear me? Still coming through.
Sounds good.
Okay, great. Thanks a lot for having me. I'm so sorry I'm not there in person. I don't normally do this. I am not an AI. I'm a real human being. um, like Alan, I often forget to introduce myself or explain what the hell I'm doing here, so I will make sure to do that. Um, Thanks a lot for having us, Alan. I really appreciate it. The opportunity to do a different kind of talk that I normally do. Normally I'm meeting with customers and sort of keeping things pretty high level. But I asked Alan, and he said this audience is pretty nerdy. So that's great. Those are my people. So I'm going to. What did you say?
I think we said technical.
Technical. Okay, sorry. Um, Technical. So I'm going to pop the hood and go through several generations of our product and how we use LLMs and share a few candid lessons that we've picked up along the way. I'm sure lots of them are things that a bunch of people in the audience have come to as well. Um, and I'd be delighted to answer questions at the end about really anything, anything you want to throw at me. Um, and I'm joined by my esteemed colleague Costa as well, who's there in person. He's local, and he's going to go through some of the infra side of things that he's had to help us scale through. So without further ado, for those who don't know what Ada is or does, I have a why is that not working? There we go. I have a video here. So we're a chatbot. That's the easiest way to say what we do. We're customer service in a box. So we make AI agents that customers deploy to all kinds of different channels: voice, email, messaging, social messaging, web chat, like I'm demonstrating here, and as well as in mobile apps. And we have SDKs for Android and iOS as well. So we have a real broad surface area that we're deployed in. And we're the front line for hundreds of brands around the world. This one's one of my favorites because I have a little 9-month-old baby at home, and this company has really put its hooks into my credit card. So yeah, check them out. But that's what we do. We answer a lot of questions every day. I'll go through some of the scale stats in a moment. But really, our whole reason for doing all this is to try to make the experience better than a human can as often as we can. And what that really means is um, AI and automation on its own is already faster than a human could ever be. It's already more available and already in many different languages than a human being could ever possibly be. But where AI often fails is to really deeply understand and empathize with customers and then know how to use the tools that are available to it to resolve that inquiry in the best possible way, including escalating to an agent when it's required, to a supervising agent when required. So what scale? We do 5 replies per second on our generative product. So we've been around since 2016. So the first generation of our product, which I'm going to walk you through, didn't use large language models because they didn't exist. But the new generation of our product, which half of our customers are now on, does 5 replies per second. That's 100,000 tokens per second. We work with 5 large language models across 3 different vendors. That's 3.5 million conversations per month. And we're growing around 15% month over month. So that's the scale we're kind of dealing with right now for our purely agentic generative product, which is the video I just shared. So the first lesson we learned is that the architecture really matters. And I'll walk you through what that really means. But architecture is so important and so critical to getting what you need out of large language models. So to start with, I want to walk you through what our platform actually looks like. I'm going to give you basically like a new engineer's understanding, or actually a new employee's understanding at Ada of our system, which I don't normally do. So hopefully this doesn't backfire. Hopefully it's interesting. So in our system, basically the first thing is we have customer contact coming into our system. This is through many different channels. We call that our communication domain. So those messages flow into the communication domain, and it finds a common denominator amongst all the different possible channels that we're in. And then, of course, there's an automation system that's replying to those messages and making decisions about whether to end a conversation or escalate a conversation to a desktop agent product. Some of these logos should look pretty familiar to at least many of you. So like Zendesk is a very common agent desktop product. That's the rough kind of flow of things, but automation without any tools or training is kind of pretty useless. So that's a big piece of, that's a huge component of our system. We take in knowledge sources. These are content management systems like Contentful, Intercom, Zendesk has a help center, Salesforce has a ton of this stuff. But it could be also just a website or a PDF. Customers sometimes just drag and drop a bunch of knowledge content they give their agents. And then we have actions. These are API actions that integrate with business systems, for lack of a better term. So this could be like Stripe or Shopify, or it could be like a database, sitting in a virtual private cloud. The other part of our system is our user profile system. And this is so important because really this becomes both a memory of the customer's preferences, as well as a way to personalize the interaction. There's nothing worse than calling customer support and having the person now remember who you are. And we've all had that experience where they ask you like a bunch of pre-flight questions and then they ask you again when the agent connects. You really try to avoid that as much as possible. So the data lives in data warehouses or these other CRM sources or data enrichment sources like Clearbook, for example. And then lastly is analytics. And analytics is so critical. It's called out as a separate component because it's so critical, because that's the way that our feedback loop gets connected. I'll show you that in a second. And then finally, there are these syncs or these places where our customers tend to want to ingest that analytics and do their own reporting as well, sometimes internally. Not always, but sometimes. We have lots of analytics features inside of our product team. So that's the platform. That's the kind of domain model. Hopefully you can kind of keep that in your head and it's not too complicated. But I wanted to give everybody that kind of grounding before we get into the architecture of the automation domain. So the first generation of our product, like I said, didn't use large language models. This was built in 2016. And it uses an intent classifier. Probably many of you in the audience already know what this is, but just for those who don't, an intent classifier takes in the text of a customer's message, like I'm having trouble logging in, and it decides that based on some custom training that the customer provides, like a bunch of examples of the ways people describe that problem, it would decide to run a workflow, like think of a Zapier or like a small program that's built with a drag and drop, like kind of no code editor. It would choose to execute a program that matches that intent. So if someone says, I'm having trouble logging in, they'll say, okay, that most best matches or most likely is this workflow about password reset. And those are workflows that are predefined. They have to predict all the ways that customers might need help. And if there's no matching workflow, then that's where an escalation to an agent would happen. And within those workflows, there are steps or actions. We call them actions that are performed in sequence. And then lastly, there's that feedback loop. So customers would be learning from CSAT surveys and performance data, and then changing those workflows or improving the training. So that was the first generation of our product, pre-large language models. That product up until 2019 used a language model called BERT, which was a transformer model created by Google. And so every customer actually had their own fine-tuned version of that model. But that model, though it was a transformer architecture, it was used as a classifier. It was most commonly used as a classifier in the industry. So it probably could emit some text, but not nearly to the extent of even DaVinci 2. So then flash forward to around 2021, I want to say, or 2020, when we started seeing the advent of large language models like DaVinci 2 coming online. This is definitely pre-ChatGPT, where we had access through OpenAI to test these models. And the natural thing for a lot of companies like ours, our competitors, as well as the agent desktop products, was to kind of just slip this thing in and say, okay, we've got this use case already, because when we don't know what to do with what a customer is asking, you don't have a matching workflow for an intent. Right now, we just escalate to an agent. So why don't we just try to route this thing to an LLM and give it some retrieval augmented generation and see if it can give a response. Sounds kind of logical, right? And there's still actually some products to this day that are being sold that do this. And the customers that like this, they like the sort of risk aversion effectively. But this in no way maximizes the experience for the end user, because maybe some of you have even experienced this. Basically, you have this split experience of the conversation. Sometimes you ask something and you get a pretty robotic response, but probably like a perfect, certainly 100% accurate response. And that's the workflow execution. Workflows are rigid, but they're made by a human with the final say on what's allowed to happen and be said. Whereas especially in 2019, you were really fighting against the model's hallucinations. So this was our first foray into building on large language models, and we learned pretty quickly the difficulties of inaccuracies, as well as just this trying to put a non-deterministic system inside of a deterministic one. It really ends up making a pretty janky experience, for lack of a more scientific term, for the user, because they have this experience of getting these natural responses that are quite personal and contextual, but then flipping back to these workflow responses that are more rigid. We quickly realized that wasn't the right architecture. Luckily for us, around the time that we realized that, and by the way, we realized that with like sort of millions of conversations. Like, we were able to get customers on this and learn at a really great scale by taking our customers from the existing product and introducing them to this. We're really lucky to have customers that are actually, for the most part, very eager to try the latest AI technology. So we're lucky to have a deep relationship with them and be able to try this stuff in production. But GPT-4 was like a real breakthrough. This was where we decided to, basically the first thing we learned was we realized that this model could reason. And it was a really big thing. This was before the model even had the ability to do tool calling. This was even before the chat API. I'm pretty sure. Someone might be call me on that, but I'm pretty sure, I know for sure it was before tool calling. So we actually realized, okay, if we ask the model to pretend to be a coding assistant to a customer support agent, it triggered some weird pathways in GPT-4's mixture of experts where it realized, like, okay, I'm a coding assistant, so I can output JSON that I'm not in charge of. There's a human agent interpreting this, but in reality, there was no human agent interpreting it. So it was reasoning about the conversation and deciding what next to do. So effectively what it was doing was it was building a workflow in real time. So instead of these workflows being predetermined by a person, we were now having an LLM creating those at basically in real time, at runtime, and then giving it the ability to even reflect on the outputs of those steps. So if it was like calling an API, it could see the results of the API, and then it could loop back on itself some sane number of times before we would prevent it from, like, it had a circuit breaker. But effectively it was able to do this, like, I think it was like 5 times originally or something like that, before giving a final output to the customer. And this was great because it could even self-heal. Like, there were a lot of scenarios where previous architectures, and certainly the first generation of our product that was classifier based, was never able to self-heal. So the input to this in terms of feedback is coaching. So that was the first thing we created. Was we basically call these, like, custom instructions, effectively, or contextual custom instructions. So now we do a lot of fancy things, like we embed these along with the transcript and context around where the coaching is given by the customer in the transcript, so that in runtime, the most likely coaching for a given scenario from the past is retrieved and passed to the reasoning, so that it improves its decision making based on feedback from the business. So this actually, like, worked really, really well. We were shocked how well this worked. There was a lot of, Kosta remembers probably, there was a lot of skepticism at that time. But now this architecture is actually pretty common. It's actually well documented, well used. If people here have used some of the open source frameworks, like, they all support this. And the APIs rapidly built themselves around this model too, which was pretty cool. And now, of course, we have full reasoning models, which has been really exciting for me to see. I'll go into some of the notes in a little bit, but okay. So that was our, and then the last step is we basically realized we need to decompose that reasoning prompt, which was what we call mono prompt, where it took in all the context, all the instructions, all the past actions, and it had to make a decision about which action to take, whether to reply, and it had to choose what text to reply with, or if it was going to use an action, it had to choose the arguments for the action or the tool. So it had to do a lot. It was like a really heavy prompt. And so there were a lot of cases where GPT-4 just couldn't quite handle it. And certainly 4.0 really struggled as well. So we ended up decomposing this even further. So now there's a planner that takes in all that context, but instead of choosing both the action and the arguments and how to use the tool, it just chooses, I need to use it. I need to use a tool, or I need to reply. And then each of these pink boxes, use tool reply, is its own prompt and has its own, sometimes even its own inner loop that it can engage in. And then each one calls the step. It's a little complicated. It's okay if that part didn't fully make sense. The point is that we further decomposed the system, the performance characteristics we needed from the models. To get that last little bit of performance from the current generation of models at a certain price that we need to meet, this is the work that we had to do further. So that eke out, call it that last 20% of what we wanted. Okay, so that was a lot, probably, but it's a technical crowd. So hopefully it resonated. I hope I get some good questions at the end. So just to recap, the lesson one is architecture matters. And really that ideal architecture is determined by the model's capability and your businesses or your use cases performance to cost tolerances. What can you tolerate? Like what is really what I'm trying to say here actually is the user experience you're trying to create should define what model you need. And then that should define what architecture should come around. But you shouldn't go, okay, in my opinion anyway, I don't think you ought to not go to, a blog and copy an architecture that don't copy my architecture because, you think it'll work or something like that. Really actually tune the architecture, make it the minimal architecture required to get the use case that you're trying to get. That's the main lesson there. So the model capabilities determine the architecture. The other lesson here was never nest non-determinism within determinism. I've talked to a whole bunch of founders about this, and they all say the same thing. The ones that have tried this, technical folks as well, like engineers. It's something about that. It's probably like a law of physics. It yields a really weird experience for you. The other way works though. You can have determinism within a non-deterministic system. You can have and we use these every day. Like ChatGPT is doing this all the time. It's using deterministic actions all the time to retrieve information, to search systems, or to use APIs. The opposite doesn't work. And lastly, I would say, sometimes you do need to use prompt decomposition, whether you want to call that like an agent routing architecture or just prompt decomposition or modularization. But I would say just only use that when you're out of other options, because it does increase the complexity of the system, makes the system a little bit harder to reason about and test. And I'll get into some more lessons here around that right now. Okay, lesson 2, evals gate improvement. Alan knows this better than anybody here, including myself. And I'm sure there's some folks in the audience who have deep experience with this. And I'd love to learn more from those folks. But our experience has been that evals are a really big gate for improvement. So evals effectively are your way of knowing that a change is not going to cause unintended side effects or defects in the experience in a set of hopefully a pretty comprehensive and broad set of scenarios where your system needs to perform well. So the goal with evals is never to get to 100. If you're getting 100, you probably haven't covered enough, in my opinion. But your goal is to not cause regressions for sure, and have a certain performance you're trying to hit. I'll go through a quick scenario here. This is a real conversation. This happens all the time. Customers type into our system stuff like this. Usually it's, we usually don't show these slides to customers. We usually show like, well, how do I change my password or something like that? But this is how people really use it. And so the system doesn't have a lot to go on. So how to buy is a real thing. And the reasoning goes, okay, this is not clear. I need to disambiguate because I don't understand this intent of the user. I should use knowledge search to find out what options we have to be able to guide that disambiguation. So I'm not just saying I don't know what you're saying. So then there's a tool call, search knowledge, let's say, and we're searching for product purchase options. Some results are returned. Let's say there's 5 documents that are returned. That loops back to that reasoning prompt, says, okay, now I understand what the buy-in options are. I can send back. This is a reasonable, what we call a single turn call and response with a bunch of tool calls. So where do we draw the bounds of our eval? It sounds like kind of a basic question, but it's actually kind of tricky. Like if we want to evaluate if this system's really working in this case, do we draw it around this and say, okay, well, given the user saying how to buy, do we get a certain quality of reasoning? Get the expected tool call? Well, that doesn't test the full experience, but that does test whether or not the system actually is using the right tools. But perhaps we actually also need to test, do the results get returned? And then you get into tricky situations where, okay, does that mean we have to actually load all these documents into the system before we run these evals? Do we have to run the evals in a representative state of the product? Do we have to include like a database, an Elasticsearch or Pinecone or whatever we're using? Do we need to call embeddings? And so the answer is actually like the right eval that we found is architecture agnostic. So the first thing we really care about is actually saying, do we get a reply that we're satisfied with? Forget about what happened in the middle. Just user said how to buy. Did we get a reply that we're satisfied with? And one thing we started doing, which was wrong, is we did string comparison. So we'd have like an eval that said, given how to buy, this is their expected response. How close is this response? And there's different algorithms you can use for doing string comparison. And on the surface, this is smart, right? Because it's fast. You can run all your evals pretty quickly if you're just doing string comparisons. But the reality is that string comparison is super weak. It really actually doesn't tell you much about the semantic meaning of a reply. So then you get into semantic distance. So you embed the responses, and then you say, okay, do these embeddings, are these embedded representations of the text actually similar? Well, that's actually wrong too, because there's a lot in call it the vernacular, the ontology of businesses that are actually really weakly covered in embeddings, even the best quality embeddings. And so like basically every business has nouns that have a totally different meaning. Like for example, Ada is a human name, but in the context of my company, it has a completely different meaning. So that also doesn't work super well. It works better, but not super well. So what you really want to do is actually you want to evaluate the intent of the reply. You want to basically say, did this reply have the intended effect? Did it meet certain criteria that we needed to meet? And you get into basically what's called an LLM as a judge system. You're actually using an LLM to compare two, let's say, call 2 replies, and not evaluating how similar the replies are, or maybe you are, but in our case, we found that to be less valuable. What we're actually comparing is, do they mean the same thing? Do they get at these criteria? I'll show you an example in a moment. So that ended up being the most important thing, was we said, okay, our evals are no longer regression tests on the functionality of the architecture of the system. They're first, given this thing, do we get the reply we expected? And then after that, what's important is a couple little signals that we look at. And one is, did the tool that we expect to be used, or the sequence of tools that we expect to be used, were they used? And sometimes we even look at the arguments, but most of the time we mostly care about, did search knowledge happen? And then did the reply happen? Oh, there you go, I got a thumbs up. And then lastly is citations are really important for us. We have to prove, we call like the burden of proof of verifiability of saying, okay, yes, this response cited this article and it was the correct article that we expected. The way these tests work is we actually have an agent specification, and the system, before the evals run, stands up these agents in a production way, and these tests run end to end through the system. So they have a totally representative, for example, like all of what we use for our embedded search over knowledge, that's all stood up, it's all proved. And so these are slower, but it's okay. We don't run them all the time. We probably run them once a day. Whenever a prompt changes or whenever they need to be run, they're run. But they're not something that's run in CI automatically on every code change the way that our integration and unit tests. So that ended up being the formula for really good evals. That's the third generation of that. It didn't go through every generation of what we did, but those were the mistakes we made. Here's a really simple example that I took from our code base of one of our evals. It's like 15 lines. But you can see that we have a success criteria. So we have an expectation, a list of expectations can be provided. In this case, the name actually just helps for debugging. So when a case fails, it's a little bit more legible to have the actual name. And a lot of these names are common, so they're actually ID'd. I didn't make you read all these IDs, but that's there. So in this case, it says ensure full understanding of the user's inquiry. So what this eval is doing is just making sure that if the agent doesn't understand the user's inquiry, it's clarifying. And you can see what the ideal response is and the success criteria. The ideal response is, again, mostly for debugging. So it's saying, okay, look, I expected it to kind of look like this. I don't think this met the success criteria. And the LLM, as a judge, can also give feedback as to why. The last thing I'll say about LLM as a judge systems, and there's a lot of great documentation online about how to use these and build these, is that they're not enough. I found that they're great and they work really well for figuring out how to do these offline evals, but you need customer signal. And so for us, that's these CSAT surveys that are shown at the end of every conversation. So we ask, did you like the experience? Did we resolve your issue? And do you have any comments that you wanted to add? Some of them are a little different. Some of them are like 5 stars. You've probably seen like in DoorDash or Uber Eats or whatever, very similar stuff. But what that gives you is a signal in real life that you can align your evals to. So if your evals are kind of like, let's say, running at 90% performance, but you've seen dips in CSAT, it means either your evals are not covering cases that they need to, and you can use this to then figure out where those cases are. You can use the user signal to figure out where those cases are, which we do. Or it could mean that your LLM as a judge has failed. And actually, like, there's something wrong with the way you're prompting that. I like this quote from Jeff Bezos. When the data and the anecdotes disagree, the anecdotes are usually right. And the beauty of this quote is that it actually came from him challenging one of his VPs of customer support, who presented him a bunch of stats on average handle times and wait times that Amazon.com customers were having. And Jeff said, I'm getting a lot of customer complaints. Like, my friends are telling me that they're waiting like 15 minutes on hold to talk to Amazon support. What's going on? And the VP said, no, like, these are our stats. They're all great. We're meeting our SLAs. So he picked up the phone and he called Amazon.com support in his VP meeting, his exec meeting, and made everybody sit there for 15 minutes while they waited to connect to an agent. It must have been a pretty rough meeting for that poor soul. But it's a great story, and I think it's true. Data can lie really easily. And we all know that because we've all had really crappy experiences with customer support. And I'm sure, like you, I've often wondered, like, does this company just like not know? Like, they all say, like, we're going to record this for quality assurance purposes. You're like, are you listening? Like, so it's because of that. Like, it's really hard. Transcript analysis, for example, is still it's a lot better because of large language models, but that's a really hard problem too. Okay, so lesson 2 is evals gate improvement. They're a really important way to make sure that as you change your system, it's a change accelerator. If you don't have evals, you don't really know if your changes are positively affecting the outcome of your system. That causes, at the minimum, a lot of chaos and fear and doubt. And in the worst case, it actually creates really bad experiences for customers. So the main thing is you want to decouple your evals from your architecture, because that architecture's got to change. It's got to adapt to new model capabilities. That's going to be the theme of my third lesson, you'll see. That was a big one for us. We had really tightly coupled evals to our architecture, and it caused us to be actually change averse. And that was like whoa. Like, we actually wiped the slate completely clean, rewrote all our evals so that we didn't have that problem anymore. Because change really matters in a software system. The rate of change, I think basically quality of software systems are entirely defined by that rate of change. Second thing is check agreement between your user signal, your anecdotes, and your LLM as a judge. That's a really important thing. If you're using an LLM as a judge system, which we have to, you have to check that signal against something real, not against another LLM as a judge. Okay, lesson 3 is embrace the bitter lesson. I can't see hands, but how many people know what I'm talking about here? Maybe Alan, you can tell me if people are raising their hand.
We got some hands, but not everybody.
Okay, all right. Well, you can Google the bitter lesson if you don't know what this is. You can do it now and just tune out if you want to, or you can do it after. It's up to you. But it's a great essay, I think by Rich Sutton, and basically the essay says every attempt that AI scientists, ML scientists have made to try and solve specific problems with basically specific solutions have been trumped by generalized solutions to reasoning and intelligence versus building specialized models for specific problems. I don't think that's probably 100% true, and I don't think he would say it 100% true, but it's been the absolute general trend. 100% been the general trend, and it's specifically in generating text and reasoning and things that are approximating general intelligence using AI. It's absolutely been true. I think this chart best illustrates it. This is from the OpenAI's O1, but this applies to all reasoning models. This applies to DeepSeek. This applies to O3. This applies to whatever Cohere and Anthropic have as well. Basically, I'll try to summarize this and then I'll go into the details of it because I think it's a good thing for everyone. But what this is the performance of O1. On the left, the chart is at training time. So this is like when they're actually making the model, training the model, training the neural net. How well does it meet these coding benchmarks? So if anyone's done like competitive coding, this is basically what it is. There's an expected output for a given problem, and the LLM has to write the code to get the output. It doesn't know what the output is, obviously, but it knows how to write code. And so this is the frequency at which it does that in one try. That's what the pass at one accuracy means. I think the eval set is called human eval, but I don't quote me on that. But essentially, it's like a code writing eval set. So at train time, it's a log scale, so it gets exponentially long with exponentially longer train times. You get a linear improvement in performance. That makes sense. Same thing on the right, but on the right, what it's saying is with reasoning models have this new way of basically being able to have a depth parameter where they get time to think before they give their completion, before they give their answer. And probably many of you, if not all of you, have experienced the new models like DeepSeek or O1 in ChatGPT, where you see like it's thinking and it has like a stream of consciousness that's kind of summarized for you. Or in the case of DeepSeek, you actually see its full stream of consciousness. So that's the model still outputting text. It's no different than the previous models. But the difference is that model is now optimized for something that approximates thinking before responding. So rather than that thinking happening within the architecture of the net before it starts generating the first token back on its completion, it's now getting a chance to kind of think out loud, so to speak, which improves the performance of the final part of the completion, which is the answer. And so what this is saying is that you're also getting the same performance as we increase the test time, the amount of time we give the model to think out loud post-inference. We're getting a linear improvement on that accuracy, on that basically the likelihood that you got it right on the first try. So this is kind of a very technical thing, but essentially it's a really big deal because what it means is that you can throw more compute at train time and get better performance, and you can throw more compute at inference time and get better performance. And so far, it's been a fairly, basically like a fairly linear curve to exponential compute. And so if we keep finding new and better ways to get that compute, with more and more flops, we should get more and more performance in these models. And so what that really means is that any clever composition or architecture, like the one that I just showed you, where we have a planner and oh, look at us, right? Look at us getting around the performance barriers with current model. It's gonna we're fully ready to throw it out. So as much energy as we have to put in to get the performance for the cost or the latency that we need right now, we also have to be completely ready in a few weeks' time to completely throw it away when new and better models come out that completely generalize that need for modularization in the first place. That's the big takeaway. So you set up your evals right so that they're architecture agnostic, they're perennial, you get to keep using them. As new models come out, you get to keep swapping them in and out, but your evals remain consistent, and you embrace this bitter lesson that that stuff doesn't really matter. Today, it's just working around the current barriers, and the current barriers will be gone in a matter of weeks or months. This is the quote. Go read the essay. You don't, nobody wants to read a quote on a slide. That's it. So new models require new architectures. Lastly is, if you find any of this interesting, we're hiring. So come join us. It's a really hard problem and a really fun one. Thank you.
Well, hello, everyone. Thank you so much for obviously taking the time to come out here and listen to us, talk to you a lot about our company and what we do, but hopefully there's, a few lessons here that we can share that are, of interest and something that you find is useful in your endeavors, whether they be, private, personal, public, wherever they may land. So my presentation here is more so going to be, I'd say, a bit of an addendum to what David just shared with us here. It's going to focus a little more on our infrastructure side. And the goal here is really just to share some of the experiences that I've went through and that our infrastructure team at Ada has went through as we, scaled, as we embarked on this journey to basically scale to eventually servicing 5 billion conversations. So let's get started here. I'm just looking for, So Ada scaling journey. David described, that we've been on this path since 2016. But there was a really clear demarcation that happened in November of 2022. And that was when we all, clearly knew that generative AI was going to be the inevitable future of this field. So that presented a really interesting challenge for us as an organization, obviously, but as an infrastructure team in particular, because we knew that there was going to be a lot of conversations that we're going to need to continue to support from our, what we consider today our declarative model, and a new way of supporting our generative conversations as well. So that meant, basically maintaining these two different systems together. However, what I really want to focus on in particular is how we kind of embarked on the journey of scaling up the generative product. So when this demarcation point happened, we knew that we needed to prioritize our developer velocity. Front and center, basically being able to pump out new features and build this new generative Ada was our number one priority, both as an infrastructure team, also as an organization. So that meant having to keep things very simple. We had to basically optimize for rapid iteration, and we had to keep our infrastructure as simple as possible, no more complex than it needs to be to service both the conversations that we have from our declarative product, while also building out how we're going to service the conversations from our generative product. And the approach that we landed on was actually to try and reuse as many aspects of the system as possible, so that we could basically be able to transfer all of our knowledge and all of our gains from the original declarative system to the new generative one wherever possible. Our knowledge gains from like a scalability perspective. So that meant our tech stack did not actually need to change too much. Really, the primary thing that was added was obviously going to be the LLM vendors themselves. Now, there's going to be some, differences in terms of how, your embeddings might scale, how your knowledge retrieval might scale. So differences in terms of, the parameters of your data stores growing. However, ultimately, they are not going to change too differently from what you're used to scaling in the previous product. So this this shift eventually started to present itself for us as a problem and a challenge that we needed to solve once we realized that our generative product was actually servicing hundreds of thousands and eventually today millions of conversations per month. As our LLM adoption started to decrease, we did start to see increases also in the performance bottlenecks that we were seeing across our infrastructure. We started to see that Infer scalability was becoming much more critical for us, and in particular, failover mechanisms were becoming a real factor for the reliability and the resilience of our product. And the reason why I say failover mechanisms, is because there was obviously moments throughout 2023 and 2024 where there were outages, sometimes pretty big ones across LLM providers, and the most commonly used one in particular. So as we started to scale, we realized the lessons that we're learning here are that there's nothing necessarily wrong with the tech that we're using. And in order to be able to provide as much velocity for our engineers to build out the product that we need while still servicing the existing customers that we have, we're going to need to build out our features in a very standardized way. And that meant, relying on managed services wherever possible. Today, our stack primarily, actually runs across two cloud providers, but we use, common third-party data stores wherever possible. We use standardized and managed, knowledge retrieval data stores like Elasticsearch, so that we have the ability to scale those horizontally without having to worry too much about some of the externalities around parameterization and scaling, scaling vertically, for example. So we doubled down on the boring and the well-tested technology. We already had some pretty good experience with Nginx and with caching using Redis, with our async processing pipelines using RabbitMQ. And we knew that these were going to be some of the foundational infrastructure components that we build our stack on. So this effectively allowed us to continue building out our product as quickly as possible while maintaining the satisfaction of our customers. Now, as we continued to grow and as some of the scalability challenges started to emerge, we found obviously through the outages of OpenAI that they were a pretty big catalyst for us in terms of moving from a single provider LLM, single LLM provider to a multi-cloud space, and also a multi-LLM provider strategy. So the biggest issue here was that obviously when we had an OpenAI outage, we failed over to our only secondary, which at the time was Anthropic, and everyone else had the exact same idea. So when your only failover strategy is basically picking between two of the really only and largest choices at the time of LLM providers, you know that you need to kind of think a little more outside the box around how you're going to solve that problem. So what we considered from our approach was, well, yes, we know that that OpenAI is able to provide, you know, the throughput that we need and everything else, but they can't necessarily provide the failover mechanisms if Anthropic is the only other option for us there. So we ended up integrating obviously multiple LLM providers, as David shared earlier. But we also integrated just multiple different variations on how we use those LLM providers. So with OpenAI, for example, we ended up using Azure OpenAI, and we used different avenues to use their models and use their infrastructure. So we would use the provisioned options, we'd use the pay-as-you-go options, and then we could also fail over to OpenAI directly. But we could also fail over to Anthropic and Bedrock, AWS Bedrock, and other variations of how these models can be provided by just the hyperscalers that we have available today. So our multi-cloud strategy was partially influenced by this fact, because we knew that to support these failovers between the different cloud providers, we'd obviously need to use the services that they offer. One of the key things that we also needed to consider here was obviously how we build out our dynamic request routing between these different providers. So lots of options are available in this space today. And I'm sure many of you have heard of, providers or frameworks like LiteLLM, or third-party providers like Portkey that can be used to help, seamlessly transition and fail over requests between different LLM providers. But in our scaling journey at Ada, we started building out so many of these processes before many of these frameworks were ever even on the market. So what that meant for us was that a lot of our tooling to switch between these providers was built out in-house from the beginning, and very much purpose-built for what we needed out of these failover mechanisms and priorities and retries and everything else. So the in-house approach enabled us to tackle really the key business decisions around the selection factors for what LLMs we use. So that means that we were able to prioritize things like the customer experience. At Ada, we support a multitude of different modalities. So if I'm a customer that's making a phone call, I'm going to have much different expectations around the amount of time that I wait for a sophisticated response than if I'm a chatter in a window, or maybe if I'm sending an email. Totally different modalities and different selection factors as a result that we need to consider for how to service these requests. So internally, that means that the technical challenges there for us were, how do we seamlessly switch between these different providers without disrupting how do we seamlessly switch between these different providers without disrupting the workflow, of our customers or the experience that we provide for them? So, like I mentioned, we built out, this platform internally to allow us to switch between the different LLM providers, and we learned a lot of lessons there around things like managing rate limits, quotas. And the importance of observability, of getting the key metrics that you need out of these LLM providers, so that when exactly you want to switch based on what it is that you want to provide. So some of the lessons that we learned here was obviously that observability and failover for us between these different LLM providers is really one of the most critical pieces. So having a lot of them available, having different providers, even if it's OpenAI through Azure or if it's Anthropic through Bedrock, is important just so that you can kind of insulate yourself against outages in any one of them. But also the observability across the entire stack is very important so that you know exactly when it is that you should be failing over. One of the key challenges I recall one of our teams was facing when deciding how to fail over when you're getting, let's say, timeouts from a particular LLM was there's an issue with how long do you want to wait for that timeout? Because if you're sending maybe, let's say, a fairly complex request that requires a lot of tokens to be completed, it's going to take longer, naturally. But if you need to, for example, let's say on a voice modality, still offer a reply within 5 seconds, otherwise the conversation doesn't look too natural, we have to consider then, well, how long do we wait before we fail over to the next available provider? So there's a lot of very specific contexts there that we had to consider when we were building out the failover mechanisms. And as a result, they've always kind of been built out in-house at Ada, and we hadn't, like I said, used some of the more official providers that are out there. It's definitely something that our teams continue to POC and investigate as time goes on. But I want to kind of mention that there's kind of a beauty almost in some of the simplicity of starting out very straightforward and just building completely to cater to the use cases that you need to cover, and not necessarily having to consider an all-encompassing framework that might be very broad and cover a lot of different use cases, but might still not cover something really specific that you need. Another lesson, obviously, from the observability was that proactive monitoring and alerting on all of our critical paths within our product is paramount. We need to obviously know when there's an issue, not just with the LLM provider itself, but with our service being able to deliver a specific functionality or feature or a response. So if you're seeing, for example, let's say you're seeing a response that's showing something that's addressing your question, or maybe handing off to an agent right away. To a customer, that might seem like it's something fine, but under the hood, if we instrumented, for example, a failover mechanism to hand off to an agent if an LLM is not available or not responsive, we need to be able to obviously understand that situation so that we can go in and see where the actual issue within the system is. So, embrace very holistic and proactive monitoring and alerting throughout your stack. And the final point here is really try, for us, it was really important to build a lot of cross-team empathy for how our product functions very holistically. So as an infrastructure team, this meant, hosting a lot of game days, inviting members from other teams. We have a bit of an internal program called Infrastructure Champions, where we try to ensure that members across teams can have some representation within the infra domains at Ada, and share some of the knowledge and learnings from our infra domain. Have some of these members cross-functionally build out the dashboards, build out the run books that we use to basically deal with any sort of failures in our systems. So the final thing I just wanted to mention before before completing here is that we don't want to necessarily forget about the costs associated with scaling to such a large extent. There's considerations obviously from the infrastructure side of the house, like, how are we scaling our Kubernetes cluster? How are we scaling our data stores? How are we scaling, our networking layer and throughput and requests? And how much does that cost? But all of that tends to pale in comparison with how much LLM costs are at that level of scale. And really the pay per token model makes cost-conscious scaling something that absolutely has to be considered. So lesson learned here was that the LLMs dwarf infra costs. Even if you can spend and invest time in, some minor cost optimizations on the LLM side, you're going to save a huge amount on your infrastructure spending overall, compared to if you were to, look for improvements across other components of your infrastructure. So obviously, probably the biggest change for us or impact for us here on our cost was utilizing provision throughput or provision tokens from the hyperscalers. So from Azure, for example, they offer PTUs or provision throughput units that you can utilize to basically reserve LLM capacity on a monthly basis. So you prepay for a certain amount that you need. And this is where the observability obviously comes in really handy. You need to know, how many tokens you're using, and of what models, and to know exactly how much you want to, in that case, reserve. And they'll give you a substantial discount basically on the LLM costs. Another strategy to consider is obviously like caching. If you can avoid any sort of unnecessary LLM calls, and basically use caching to provide deduplication of requests to LLM providers, that's going to have a lot of dividends to pay down the road. It's something that we're continuing to improve at Ada. But even if you can, make a jump from caching 2 or 3% of your responses to 5 to 10, on the whole, in LLMs, in terms of costs with LLMs, that's a huge line item compared to some other areas of infra spend. But that being said, the infrastructure piece is still important. I just want to make a call out here, kind of like more generally. There's different aspects of infrastructure that still need and should use we should still invest effort into optimizing costs for. So at Ada, we tend to utilize preemptible or spot instances as much as possible for our compute layer. We're very lucky that we get to keep most of our compute layer relatively stateless. So that means being able to take instances in and out of existence is something that's very important for us and really valuable from a cost management perspective. Also, that enables us to use auto-scaling strategies both on the compute layer, but also on the data layer to some extent. When you're thinking about, some of the clusters that we utilize for our data stores, whether it's Elasticsearch or MongoDB, having the opportunity to scale those up with demand is very important. But being able to also scale them down when you need to, or if you see that there's maybe an opportunity to, remove some chunks of data from your system. It's when you're dealing at a large scale, it's something really valuable and worth considering. So that's all I wanted to really mention here about the infrastructure layer. Like I said, more of an addendum to what David was talking about. But yeah, hopefully some of these lessons can show you that a lot of what we do at scale with LLMs doesn't necessarily have to be all about the, latest and greatest frameworks. We can just do so using, the more boring or sometimes more practical approaches to just tackle the problems that we have at hand that are most pressing for our customers. So if that sounds interesting to you again, just wanted to end on the same token that David did as well. Thank you all so much.
All right, we've got some time for questions. Do you want to be our mic person or should I? We got hands.
Can I go first?
Yeah, Travis can go first, and then we'll take Neil next.
Wondering if you can talk us through the story of what an incident looks like when you're dealing with LLMs in the background, non-determinism, and shit hits the fan. How is it different from a deterministic shit hits the fan situation, and how do you deal with it?
Ooh, that's a great question. So in terms of what's different, I would say it's primarily how do you instrument the fallback mechanism? Because when there's an issue with a deterministic problem, we know exactly what part of the system we might need to look into right away and figure out. When it's non-deterministic, we know that, hey, maybe there's a more significant change here that we need to consider making, and we need to try to really understand, like, was it something that we did, or is there potentially an issue or something unexpected, a bad day that ChatGPT is having or something like that. So I'd say the most challenging part is really diagnosing the issue and understanding, like, is it is it something that we're actually that we can fix right away through like a code change, or is it something that we're going to need to understand more deeply and ultimately improve through our product? Yeah.
Hey, hi, my name's Neil.
Hi.
So many questions, but I'll start with one. Is you described a really complicated world where, like, okay, there's this software as a service AI and this one and this locally hosted one, and then another fallback strategy. Maybe we'll even use some of your older techniques that you're not LLM based. Is this picture getting more complicated or less complicated in the short term? Because we have now some really powerful, fully open source models. Where do you see this going in the near future?
Love to hear your take as well, David. From my perspective, I think it's relatively so our system is in a relatively good spot where we've got most of like the edge cases that we need covered. In terms of how complete the solutions are today, I think it's I think there's always room for them to grow, but the interesting thing is that they've become much easier to work with in the sense that you can simply just swap out different LLMs as you need to, and that part really helps to kind of like reduce the tech debt aspect of what it is that you're building.
So you see a value in the swappability of every part of the system, even if in some future world you might be running on just one LLM.
Yeah, definitely.
We plan to basically the core of the system is getting simpler as better models come out, as long as they're at a certain performance characteristic, which is like price per latency. So that's what I see in the future for our system. Whether we use an open source model or a closed source model, we're sort of agnostic to. Like, we'll use whatever is the best solution for our use cases. But the thing to note about that is that the problem keeps getting complicated at the same time. So the breadth of the problem of customer service automation, basically the way to I always think about that is that the reward for doing the job well is more jobs, more work. And so you get customers basically like, okay, great, now answer email. They're like, now answer phone calls. Now give me a UI where I can manage the automation in one place across all three modalities and reason about my analytics and my sources of feedback on these three very different experiences that have very different performance tolerances. On email, it's okay if you take a day to reply, but well, not a day, but a few hours. On voice, customers are really sensitive to even taking a second to reply. And so building a system that's able to do all of that and tune the models to be able to perform in those three very different scenarios that I gave as an example. And then, of course, as we look to the future of our company, there are other places where North American businesses are being forced to outsource some of their business, whether it's like data entry, for example, or other use cases like that, where the experience for the customer is worse. And the business doesn't really want to do it, but they're being forced to. And so we think AI is going to make that better for everybody. And we're pretty excited about being able to bring our platform to those use cases too in the future. So the problem gets more and more complicated as you grow, but hopefully the system at least maintains a certain steady cap on complexity. That's what we try to fight.
Awesome. All right. Next question. Michelle.
Yeah, David, you gave a great overview of your, chronology of your architecture, like ripping everything apart almost. I'm sure it wasn't that, simplistic. So what aspects of your previous architecture do you keep? Like you had your previous like intent classifiers and stuff. How much of that is still in the system? Because I imagine it's not just, everything's an LLM now. So just some, insight on that.
Yeah, well, I mean, from an infra perspective, Kosta knows this better than anybody. There's still an enormous amount of traffic flowing through that old the legacy system that I described. That's because those customers are still satisfied with that and still trialing out and still deciding on what their internal strategy is on adopting generative technology. And so we're working with them on that. I think in the next couple of years, that'll all be moved to generative. But even within generative, within those generations of the architecture I shared, the pieces of the system that remain the same, the main one is that knowledge system, which I didn't actually really go into too much detail on. But there's a whole way that knowledge flows from an HTML page or a PDF or some other type of content. Maybe it's something we have to do OCR on. And then it gets chunked and embedded and indexed. And that's a whole other system that's remained actually pretty constant. There's been changes that we've made to improve retrieval, but it hasn't evolved at the same rate as the core automation. So that's one piece. The other piece is the action system. So the way that business systems integrate with our platform remain the same, which is great. That was a really nice win that basically tool calling was a one-to-one map to our block system, which was like a drag and drop workflow building system. So those are just registered as tools. So when we knew, okay, the future of doing our job is going to be agentic and a reasoning-based architecture, we took a look at the whole product and we went, do we need to rewrite all this? Or what part of this is common platform that these two products can share? And we found that it was like more than 50% of the code base was common platform. And that guided our hand. That's how we decided what to do. And that ended up being the right call. There's a lot of friction. I won't sugarcoat it. Like every day we have to make decisions when we're building new functionality into the system. Is this common? Do we have to refactor it and bring it down to common? Is it platform? Do platform consumers need to be able to use this thing? Or is it just generative only? So coaching, for example, is like a totally new primitive that we had to introduce. That's a little bit into the kind of way we make decisions and the product management difficulty.
Awesome. Thanks, David. This is Alan. I'm going to cheat and ask my own question, but I think it's a fun one. So you, in between the two of you, mentioned a couple technologies that were helpful in your scaling journey. You mentioned RabbitMQ. It seemed like Elasticsearch had good vibes, so implicitly. Was there Medium vibes? we all, people building other systems love to hear from folks that have built to a larger scale than we have about any maybe tools or platforms or things that you've used that maybe cause a little bit of heartburn that were maybe, I don't know, you don't have to throw anyone under the bus, although you can. Any tools that you sort of trialed or got to
I
sort
don't
of
know who's in
scale?
the audience.
It's just us. You can tell me, David.
Yeah, sure. I'll throw some stuff under the bus. Why not? I effing hate Kafka. I can't stand it. Honestly, this whole idea that you can use change data capture from your application state store, like whatever database you use, Postgres, MongoDB, whatever. You can stream all the changes to the rows, and now you get a magic event bus that you can hang anything off of, and you can have all these different topics on the changes, and you get analytics for free. That has not been my experience at all. Like, unless you've perfectly designed your application's data models so that they also work as events that you can hang tasks off of, and they also happen to be also great at OLAP for analytics purposes. This is like a complete false dream that I think is totally self-serving Kafka, but is like completely, it just creates complexity, toil, and chaos. So my experience has been, do the simple thing, like in your application, whether it's a monolith or not, make your schema explicit for your data models, make them separate, no big deal. Write them to something like ClickHouse, do it on the same task queue you're already using for async work.
I love it. Simple. I think I heard Weston had his hand out for next. Oh, there's Weston. And then we'll do one more after Weston. Sorry, I know there's a lot of questions.
What? Wait, Kosta, do you have any technologies you want to completely throw in the
bus? Not particularly. There's a lot of technologies.
Kosta's too, he's never gonna.
There's a lot of technologies that we use that we wish we could use better. I think one example for us is MongoDB, where we scale MongoDB horizontally, but not in a sharded fashion, more so in like a partitioned fashion across different distributed clusters. And a large reason behind that is because we don't want to yet, we haven't yet at least had our hand forced to solve the sharding issue. So yeah, being able to kind of push that off as long as possible is one of those, areas of tech debt that I think we're happy to leave as tech debt in that case, just because it's such a monumental effort to have to go through your entire data layer and think about how you want to start like sharding out your customer data across multiple individual MongoDB clusters. It also becomes extremely expensive as well, especially when you have to deal with like enterprise DR strategies and have like hot standbys and things like that. So we try to avoid some of like the harder scaling problems if we can, and if we see like a reasonable path around them, where the reasonable path in this case is we've gotten really good at just building out additional environments, and that seems to work really well with like our global scaling strategy as well. So being able to just kind of build out cookie cutter, like Kubernetes plus Mongo plus Elastic plus all of our other data stores in chunks in different regions in the world across different cloud providers, that lets us hit the scale markers, I think, in surprisingly a more achievable way, and in a way that's at least more standardized and easier for our developers to work with, because we try to automate as much of that factor as possible. But the data layer, sharding a data layer is hard to automate.
Sharding a data layer is hard.
So this is,
I'd say vector search with Pinecone would be really nice if we could use that. There's reasons we can't, but if you were starting from, if I was starting again from scratch, I'd use Turbo Puffer, Pinecone for vectors.
all right, I'll try it back
I
here.
think you're good. Yeah.
So this is a follow-on question to Alan's question, like where there might be dragons hiding in these architectures. And you had a point where it was in all caps. You said never put a non-deterministic thing inside of a deterministic thing. Can you give us an example of what you meant when you said that?
Yeah, for sure. So the example I tried to give and is very specific to that architecture back in 2019. But basically, the example is where you have an intent classifier who's taking in a customer's question and trying to figure out, okay, where do I route this question to? And that's not using a large language model. That's just using maybe support vector machines or some other neural net architecture that's not generating text. It's generating a probability and a bunch of IDs, and the IDs correspond to workflows. If you try to throw a large language model into there and say, by the way, if you can't find any of these workflows that match in any intent, then let the LLM. The end user experience is they're getting like essentially a super robotic workflow driven experience, and then they're getting these really natural replies when there isn't a workflow to match. That's kind of the best case. The worst case is that the two systems are fighting each other for control of the conversation. So that's one example of where we realized this. We don't have a lot of other examples because we've felt this so viscerally. We just really despise the experience we're providing when it failed. That we just wrote this down as a rule and kind of never went there again. But I can sense that the example is not necessarily clicking. So I'm trying to think of ways to maybe rephrase it or change it. Yeah, I don't know, Alan, maybe you can help me out here.
Yeah, we mentioned, David, that there were other founders that had had this similar experience when you related. I'm not sure if you can remember it, what the basic shape of that was.
Yeah, I remember talking with Alex McCaw, he was the founder of Clearbit, and now he has a journaling app called Reflect. And he encountered the same problem. And I think Notion did too when they were building their AI thing. And again, it's probably just these software systems that have some kind of classification under them, or maybe like they're using Elastic for search, and then they're trying to use a large language model as a fallback to that. And I think that's probably the biggest problem. And so what you want to do is flip it and actually put the large language model as the governor. That's probably the best term for it. And the governor can decide, like, look, I don't know what to do with this thing. I better use like some kind of fallback mechanism that's fully deterministic. And that ends up being a much better user experience. That's really where that's coming from. It's not necessarily about like the complexity of the system, although it is quite complicated. It's not really about the testability of the system. It's actually just more about providing a great user experience. And so really what that comes down to is the consistency of that experience. And it gets eroded if there's two systems fighting that are fundamentally different. They have different trade-offs. A deterministic system, the trade-off is any possible state that the system could be in. So you can test each state, you can give guarantees to customers of what those possible states are. A non-deterministic system trades that off, usually for the quality of the experience, hopefully for the quality of the experience. But you have way less predictability over the possible states that it can be in, which is like basically hiring a human being. Hire a person, you have no idea the range of possibilities, nor could they even tell you. But you have certain trusts and guarantees from our processes around interviewing people and just the kind of general vibe they have. So that's probably the best way. Does that make sense? Does it click or no?
Yeah.
I can keep going.
No, I think it makes sense. And we have evals for humans too, right? I know I said one more question, but we're running shorter than on time than I'd realized. We're supposed to be out of here by 8. So I'd like, and Kosta, I will probably be able to pin him down for further questions after that, or maybe even no promises out for drinks after. So everyone, please give a big round of applause to Kosta and David. Thank you so much.